We are welcome to again to this afternoon class. It's a pleasure meeting you once again, the third day of my course. We will continue because, as you know, that we have been discussing about Hamilton Ricci flow and the Li-Yau Differential Harnack Inequalities. Okay, so we'll continue in that direction. On the one, we try to give a background on the Riemannian geometry, and we introduce Ricci flow, and we showed examples, but geometrically we show, and we work out some example. Then yesterday, we started with, this is what we discussed yesterday. We discussed about special solutions to Ricci flow, the solution that's self-similar solution to Ricci flow, and we show how important they are to Ricci flow, that their special solution, in fact, they are modeled in the study of a singularity of Ricci flow. And then we discuss about the existence and uniqueness of Ricci flow, short time existence. We try to show that, okay, Ricci tensor is a differential, second order differential operator. And we try to fill Ricci flow as its equation. Then we saw that it is not strongly parabolic, and then it's difficult to just take theory from PDEs to say, oh, we want to show existence. And that was why in the original paper of Hamilton in 82, it used some tools from functional analysis, which we explained. And we now say shortly after that, there was a paper by de Tocq, which is popularly known now as the de Tocq trick, a way to take a modular the diffeomorphism invariance in Ricci flow so that we can have a strongly parabolic partial differential equation. So in order to use theory from a PDE to show short-time existence, that was what we discussed yesterday. And again, we talk about evolution of geometric quantities. Yes, we brief that again. That was where we stopped yesterday. We'll go over through that again in order to start today. In today's lecture, we will discuss about the maximum principle, which is another powerful tool that is used in the study of a Ricci flow. Then we will talk about the curvature derivative estimates, as this helps in the showing that curvature flow-ups in a finite time, and how we can extend Ricci flow past the singularity time, okay, which in a way helps to show long-term existence of Ricci flow. Okay. Let me quickly discuss about this. Again, as a way of introduction, I'll give the Ricci flow. Again, we know G is time dependent. So we say we have a family of time dependent smooth Riemannian matrix evolved by two of Ricci tensor of the metric. So this is Ricci flow with initial condition G of 0, G naught. Okay, that's Ricci flow. Now we want to discuss how quantities under this Ricci flow how they evolve, especially what is interested to us that we use. We want to see how well metric inverse which is a Gij, how it evolves. Okay, you can write this in local coordinates. Well, there's a Gij so that it can And at times I can write this as Rij. So want to see this? And then how Christopher symbol. How it also involves. Okay, under the tree flow, we can then how the Riemannian curvature tensor evolve. Curvature tensor. Okay, which is maybe Rijkl. What of Ricci curvature tensor? The scalar curvature. Another important thing is geometric quantity is a volume element. If you remember, we define this, maybe we define this as a determinant of a matrix, okay? I think we define this. This is a wedge product of Xn when your manifold is adimensional. So we want to show this. Then we say in a way to show this under Ricci flow. You want to see how each of these involve other Ricci flow. A way to show this, we say, okay, let's start with an arbitrary duration of metric. And as we have it here, let's say our metric, the metric now involves with H. Hij, which is a 0,2 tensor 2, is of a Ricci tensor. Good. Then we mentioned that okay, this is the lemma. We say suppose you have this family of metric involve under this flow, okay, arbitrarily, then the inverse of metrics evolve this way. Okay, and we try to show that. Let's show that again so that we can. We say, okay, now the arbitrary metric variation. So we said, okay, if you have D of G, Ij evolved by Hij. Now, how does a metric inverse evolve? Then we said we can write a metric inverse. Okay, so this is starting from here. If you have Gi, Gi, okay, there's a Kl is equal to direct delta or chronic delta Ik, okay, this way, which can be 1 when I equals to K, and we can be 0 when I is not equals to K. So you have that, and you can do differentiation of this. Differentiate this one with respect to this time, and differentiate this. This one becomes 0, and this one look this way. So you have the derivative of this. Oh, sorry, please. So from here you have differentiate this. This going to give you a derivative of, so you do this, that's a product. So derivative of G, K, so you have this, and well, just take this one to the other side. You see that manual this becomes the T of this, this GKL, so this is what you have, this, okay, is minus of GIK. Then you know this from the definition of this. Okay, variation of GIJ is HIJ. So variation of GKL, that is HKL. So that is how you arrive at this. You can just vary this. Maybe you, let's say you will have this inverse. This you trace this, which is a way of contracting the index here, and you can have this. Okay, to show that, let's say GJL. Okay, so which means you this one also minus GJL, and that is how we have that. Okay, then as well, the Christopher symbol. We know the value of Christopher symbol. We can do that as well. The Christopher symbol is given by as this. Yes. Okay, let's use this. There you have. So this is Christopher symbol. And then you can find the variation of this, which is variation of this with respect to this. And I will say that's going to be, so you have this. So you want to variation of this, that's going to be a product rule. So you have 1/2 variation of the this GKL, okay, this multiplied by this quantity. Let me write it out. Then plus, you have this quantity 1/2 GKL, then variation of this quantity. Okay, so by time this one, we already have this from the variation of inverse metric, which is this guy. Okay, then variation of this here, this quantity here, that is covariant derivative, so it's not time dependent. This GI is time dependent, so you can have variation of this plus covariant derivative of variation of GIL minus covariant derivative of GIL. So by the time you spread this, then you just have this one inside, and the variation of each of these is H from the variation here. Then you apply working in normal coordinates, then some term cancels out, and we have this. Okay, what is on our screen? Let's do that. Then again, we have Riemannian tensor. It forms as this. Yes, maybe in our first lecture, we expressed this Riemannian tensor in form of Christopher symbol. So it will now be easy to do that if you can write Riemannian tensor in form of Christopher symbol. We already have the inverse of we already have the variation of the inverse metric. Here we have the variation of Christopher symbol. Then writing curvature tensor in form of Christopher symbol, we'll be able to get that expression. So it's just a calculation. These are very simple, straightforward differentiation. Then we have this, the same thing here. Ricci tensor. Ricci tensor can be written this, okay, Ricci tensor Rk. We say Ricci tensor is tracing of the coefficient of Riemannian tensor. So you have Riemannian tensor already. If you trace that, it is GJL of RIJKS. This is a Ricci tensor. So if you want to find the evolution of this, evaluation of this, you just have this, okay, which is evaluation of this. Okay. VGL, the evaluation of RIJKL. So we already have evaluation of this, we have evaluation of this, so we can just substitute and do rearranging. You add some term and subtract some term, then you have this expression. Okay, for scalar curvature as well, scalar curvature is the tracing of a Ricci tensor. The scalar curvature, I just G there just to denote that scalar curvature of the matrix G. Scalar curvature R is the tracing of a Ricci curvature. So you can have scalar curvature as GIK of RIK. Then you have this. So then we can do that. Derivative of this. Yes, it's going to be derivative of this multiplied by this, then this multiplied by the derivative of this, just like the way we have this. And we already have the fraction of this, when we substitute, we have this. So this delta square here is the second order. Okay. This quantity here. Second order fraction of H, because you have there. Then the volume element as well. Okay, I wrote the definition here. Then also we can do the same thing for the fraction, and this is what we have. Okay, in terms of when it evolves by this. So what we just do now, if you have this, then we can move ahead and do fraction of all this under Ricci curvature. We can do fraction under Ricci flow. So we did it. What we have calculated here is under arbitrary variation, but now we can do it under Ricci flow, and we don't need all the. Once we have established this calculation, all what we need is under arbitrary variation. We have Hij. Then for this to be Ricci flow, you just need Hij equals to minus 2 Rij. So in each of these, wherever with H, we just put in minus 2 Rih. Then we can get equivalence of all these under Ricci flow. So that is the next theorem we have here for metric inverse. Metric inverse involves this like this, that Ricci flow. Crossover symbol evolve this way. Volume elements evolve this way, and as well the Riemannian tensor this way. Okay, this V that we have here is expressed this way. Okay, and the Ricci tensor evolve this way, and in fact, what is observation that we can take from here? Okay, let's look at this corollary. Let's take a Ricci curvature and the scalar curvature as an example. If you look at each of them, this is a Laplacian. Each of them involves like a heat equation, like a nonlinear heat equation. Okay, for the Ricci flow, you have something You have this. Then plus some terms, which involve, which we can see there. Plus some other term. Okay, we have, let me just write it, I, J, R, minus G, P, Q, and some other term. So you have that. So this now look like its equation. The same thing under the scalar. It gives you this. Then plus another term. This. So if you look at the full tensor, I mean full Ricci tensor is also like that. So this is telling us that geometric quantity, especially the curvature tensor, look evolved by its type equation. Then, if, as we said yesterday, that we may want to put some control on all this curvature, okay, they look like each equation. There is some principle from it that we used to study each equation from a partial differential equation can be applied to do this. And that is what will lead us to the next, because we want to, for the study of Ricci flow, we want to put control on this curvature tensor, because they are the one, like we said, okay, at some point the curvature blows up. Okay, the curvature, I mean, become bigger in some cases, and in some cases the curvature shrinks. Okay, so how can we control all this? Okay, so we can do that using maximum principle. We'll be able to control this. So that is what we want to study next. We want to study maximum principle, which will help us to one of the applications of maximum principle here. Maximum principle is used in many areas here. Okay, even like a differential Harnack inequalities that we will still consider, we apply maximum principle in some area. Many aspects of this Ricci flow, maximum principle is so useful. But one of the applications is this curvature estimates. Okay, maximum principle is a key tool that is used to understand the behavior of solution of the Ricci flow. Yes, maximum principle is also very powerful, which can be used to show that pointwise inequality on the initial data of parabolic PDEs are preserved by the evolution. As we have already discussed, when metric is for by Ricci flow, like I've just showed, various conveyor tensor also satisfy system of PD partial differential equations. So the main application of the maximum principle here will be to prove that certain inequality on the tensors are preserved by the Ricci flow, so that the geometry of the evolving matrix is controlled. And consequently, we can obtain estimates on curvature and show that Ricci flow preserve non-negativity of curvature tensor, maybe in some dimension K, maybe dimension 2, dimension 3, at least we'll see that here. The maximum principle was developed for tensors by Hamilton in his 1982 paper. So what's in this sense, as we have been doing before, we still take our M to be compact without a boundary. So we say M is a closed manifold, and the metric on it is time dependent. Okay, so which varies with time. Now we want to have consider this general reaction diffusion equation, which is of the form as this, so that makes sense software. So we want to let me write it in this side here, so that I will not clean it. Let me to put this on this side. Okay. So we want to consider a general reaction diffusion equation of this form. And I want to write it here because we Well, we use inequality here for the y plus okay. This is a E-type equation. Well, if you put equality, you say the equation, but this inequality is just well, you can say it inequality. So it's a E-type equality. It's a reaction diffusion equation. You can see the diffusion part, the Laplacian here, and you see the reaction term. Okay, so we want to consider this because most of the equation, in fact, if I have not erased them, looks this way. Okay, you see the diffusion part, okay, and you have this other part. That is what you have if you consider the case. Let me put equality here, because as we move on, we may use less or equal to, or we may need greater or equal to. So you can see let's take this as an example. This is the evolution of a scalar quantity. You can see it's look like this in a way. You have this part, you have this part, while this part is just this. So this is what we want to consider and to do our maximum principle. In this case, U is a time-dependent function, okay, on M. X is also time-dependent vector field. YF is a function, okay, from this R cross this time interval. It's a real value function as well. And in this case, we are going to put some condition on this. This F should be continuous in time, okay, and Lipschitz in U. So be Lipschitz continuous in U. So I think, okay, it's already here. Okay. Yeah. And our aim is to discuss scalar maximum principle for each type equation of this form. Okay. Let's give this, this is the maximum principle, the theorem. Suppose you have U, which is a smooth function from this M cross this interval, the real value function, we satisfy this each type inequality. Okay, I've dropped F for now. Let's just see a reaction diffusion equation here. Let's see this Laplacian. This is Laplacian. This GT here is just showing the metric dependency of this Laplacian. If we understand it, we may drop this G, just Laplacian, which is Laplacian Perelman operator, because of its dependence on G, and G is a time dependent. Okay, so this Laplacian also has a way for which it involves under Ricci flow, because it's anything that is time dependent under Ricci flow evolves as the matrix is evolving. So we have this is inner product, okay, which is dependent on the metric as well. So now the statement of the theorem says if there exists, let there exist a constant alpha now, a real value alpha, such that U at time t equal to 0 is less or equal to alpha for all x in M, then U is less or equal to alpha for all x and C. So if you start with this U, this initial value, which is bounded by this alpha, the maximum principle says this, or your solution will be bounded above by that alpha all through the existence of a flow. So that's the statement here. You have this equation, just like some other PDEs, okay, but in this sense now, manifold, you have this kind of inequality, okay, or maybe you have equality and you want to say sub-solution or super solution. We are still going to define that, so we can have that, okay. So that is the statement of that theorem. And the theorem also holds if we reverse this inequality, okay, if we reverse this the first inequality in equation 7, then we are going to reverse the inequality of this this quantity in red, the first red and the second red, then the maximum principle also hold. In some places, they will say minimum principle, maximum principle, but generally we can say maximum principle. Okay. Now this, well, let's quickly go through the proof. As usual, we can prove by contradiction. Okay, to make it simple, let's start with just only the it part, the diffusion part. Okay, let's say you have this, and what I've just done is I just drop, which I will say I drop this inner products part. Okay, I want to drop that. Is trivially affect the result. So we want to prove that maximum principle in its simplest form, just this. Okay, and what we do here, in order to show that if you start with this, with the, let's look at the theorem again because we just need to understand. With this initial value, u at time t equal to 0 is alpha, then u at any time it will be bounded above by alpha. So that's what we want to prove under this. If you have together with you have x0 is less or equals to alpha, then you say that u x at t is less equals to alpha for s comma t in m comma a0. I think it's t included. Okay, let's even include it here. Then here is for all x in m at t equal to 0. So that is what we want to prove. And now to prove that, well, use this epsilon regularization. So let's say we have epsilon, a small number greater than 0. We can divide u epsilon to be u minus epsilon multiplied by 1 plus t. And by their potency, this u epsilon is still less or equals to alpha at t equals to 0. So it's this new u epsilon here still satisfy the hypothesis of the theorem. Okay, so we can now say u epsilon x comma 0 is less than alpha. So, and our claim is that u epsilon x t is less than alpha for all t. So if you do that, then you have this. But we are now introducing another new u epsilon, which is u minus epsilon 1 plus t. Okay, so we want to now prove that this is our claim, that u xt should be less than alpha all the time. So, okay. Then we can now prove by contradiction. And by contradiction, you now suppose instead of less than, okay, suppose it's greater than alpha, what do you have? Since m is constant, then you have a point where this will reach its maximum, okay? And at the maximum point, there are certain things we know. What we know at that point, the point of maximum is what we note as x1 t1 here. At maximum, the time derivative of u epsilon is greater or equal to 0, okay? And that local maximum, the Laplacian of that is less or equals to 0. In fact, that is from our second derivative estimate, okay? In the normal calculus, the second if you have a function at the maximum, okay, the derivative of that function at maximum, okay, let's use gradient now. The gradient of maximum at maximum is 0. Why the second order derivative, which I will use as Laplacian, is less or equal to 0. That is maximum point. If it is minimum point, you still have the graded equal to 0 and this greater or equal to 0 at the minimum. So that is what we have here, and making use of that. Then combining this and this, okay, into this equation, we have this. This is less than 0, less or equals to this minus, okay, this epsilon. This is the way. Let me just show the way we have that. If you have this is our epsilon. You can see that u epsilon is u minus epsilon into 1 plus t. So you can have the u epsilon, the t, to be the u dt minus epsilon. So that is what you have here. So this guy gives you this guy. And because minus epsilon is positive, so minus everything here. Okay, let me quickly write so that we can see this line. Okay, we have, let's take this. We have this, the u epsilon dt, okay, is greater or equal to 0. This implies the u dt minus epsilon greater or equal to 0. Then we have, let me write it here, u epsilon less or equal to 0. So combining this, we have a 0 is less or equal to the u epsilon dt. Okay, if you have the heat equation, where is it? Okay, from here, this guy is less than the u dt minus epsilon, as we have written it here. The u dt itself is Laplacian, is less or equal to Laplacian of u from the equation. Okay, less or equal to Laplacian of u minus epsilon. Meanwhile, this is what you are having here. You already have this is less or equal to epsilon, which satisfies that. And because that is less or equal to everything you have here is less than minus epsilon. Epsilon is greater than 0. So you have this is less than 0, which is a contradiction. So therefore, you have u epsilon less than alpha. And since epsilon is arbitrary, well, you can say u, not u with epsilon now, sending it to 0, you have u is less or equal to alpha as required. Then you can now see from what I have explained here, if I include this, if I had included this, okay, as we have it from the equation here, so at the maximum principle, this term will be 0. So I will still have this guy. So that's what I mean by here. The proof is carried over directly to the proposition itself, which included that the term like this, there's a term like this, and at the maximum, this guy vanishes. So we have that. Okay. Then there's another important thing here. That's maximum principle. We just browse over that. Yeah, we have the same, this operator, we just say it's L. It's operator taken from what I wrote in this corner. Okay. And I have this condition on this. This is a general nonlinear second order parabolic equation here. Okay. F is continuous in T and locally Lipschitz in X. So we give this definition of a super solution and sub solution. So if L of u is greater or equal to 2, T is included in L here. Sorry, this L and this L is the same thing. Okay, this L and this L, they are the same. T is included to show the time dependence of this L. So L is defined as just this. So what we have here is still parabolic, is a reaction diversion equation. So if you have sub-solution on this, this is if this is greater or equal to 0, U here is called super solution. And if it's less or equal to 0, it's called sub-solution. So the comparative principle says, okay, you have two continuous, you have two smooth functions, at least C2 functions, okay, and satisfy this inequality, U and V. So this LU is less or equal to LV on this space M cross the interval of time. Okay, if you have this, then, and you start with this condition that V is less than U at time t equal to 0. Okay, then U is less or equal to V all the time. Good. So that is what the theorem is saying. You have that, you have LU less or equal to LV with this condition at the initial time t equal to 0, then U is less or equal to V at all time. The same thing if the inequality is also reversed. And that can be proved also, the same, similar to the way we prove a maximum principle. So this maximum principle, just what we just do is that to use that maximum principle, we define a new function. This is what we want to prove. Sorry. So we define N as this. Minus F. Okay, let me just put U here. LU. Okay. We now said, okay, if LU where U, V are C2. Let me just put that way. With this condition, if V less than this, then or for time t. So, and we now say, okay, if you want to do that, define to prove that, define any function U to be U minus V. Okay, so if you have that, you can have this expression here and see something like this, L of U minus V less or equal to 0. Okay, so which is a LW less or equal to 0. So we are handling this and look like the maximum principle that we have done before. We can do that and show that this quantity actually less or equal to 0 with that condition. Then you have U is always less or equal to V. So, and that is what we have explained here in this proof. Now, we are to state the weak maximum principle now. Having established the maximum principle, yes, comparison principle, we want to state weak maximum principle now for this, either for super solution or sub solution. And the statement is what we have here. Okay. Suppose you have U, which is C infinity. Okay. Well, C2 is okay for us because the highest difference operator you have here is just a Laplacian, which is second order. So it's C2 in M and at least C1 in T. So it's okay for us. If you have that with the condition that F is Lipschitz, is locally Lipschitz, okay, in X, then you have this ODE, okay, let phi, okay, be the solution of this initial value problem of ODE if U is less or equal to alpha at T equal to 0, then U is less or equal to alpha for all X. So this application of that comparison principle, now you have partial differential equation. Here you have ordinary differential equation. So you are now saying that, okay, if the initial value for this initial value problem, which we know here, if U is less than that alpha at the beginning, then throughout the evolution, U is less or equals to alpha of T, which is the solution of this initial value problem. Okay, that is what the theorem is saying. And well, the proof also follow the same procedure. So, and you can see here. So what we just do here, we apply that comparison principle, but in this case, we use U and phi. Though U is just a function of T alone, while V, yeah, okay. Why our U here is a function that depends on X and T. So if we look at the initial proposition with phi, okay, V will be this. And then we can now do this type. From here, LU is less or equal to 0. And here, L phi is equal to this minus this. That means L of phi is equal to 0. Okay. So using that, you have UX equals to 0. Okay, at the beginning, this is the condition. Let me just write something on the board so that we can see what we are doing. Let me give us the next line, and you see it clearly. Okay. So we now we start with this. This is given. And this OD is also given. With this condition. So if you have US, 0 is less or equal to alpha, okay, for X in M, then UX, T is less or equal to phi of T, okay, which is the solution of this initial. So these two things are given, this and this. So a way to do that now, this is now take this as a L phi, which is just, in this case, is just the phi dt minus f of phi comma t. That's what we have there. So you can now have comparison of U and phi. LU, okay, and that of L phi. So if you have to compare this, then application of this maximum principle, is it? Yeah, will be in order, and will help us to do that, to prove this theorem. So that's it. This theorem is very, very important in some of the examples that we're going to give now. So, and it's so useful in estimating curvature tensors, even scalar curvature under the Ricci flow. Okay. Then we make the remark that a similar result holds if the inequality is reversed. Okay. Yeah. Strong maximum principle for scalar tell us, in fact, if u x is less than phi of t for all t, okay, it tells us that you have this u equals less than this unless you have the equals to. So the weak maximum principle is the one involved less or equals to, but the strong one is always less than, except when you have the equality. Okay, now let's give this example, okay, of maximum principle to show band on the scalar curvature. We can also get band on the Ricci curvature. In fact, there's a special strong maximum principle for that, which is called maximum principle for tensor. I will show that as well. Maybe we quickly show this. Okay, let's stay in order. So by applying the maximum principle on the evolution equation of scalar, Ricci, and the Riemannian curvature, you can get some preliminary controls on how they evolve. Okay, for example, now let's look at how scalar curvature evolves under Ricci flow. And we want to get a control. This is the theorem that says any initial lower band for scalar curvature is preserved under the Ricci flow. In fact, it is a maximum principle that we use to do that. In fact, okay, the proof is even stated here. Okay, let's say you start with a flow with the initial condition at time t equals to 0, and the scalar curvature is this. Okay. Now, if you start with initial curvature, your metric, the metric that you want to use for the Ricci flow has certain initial scalar curvature. Then they say that initial value is preserved throughout the flow. Let's say at the start of the flow, at the start of Ricci flow, the Ricci curvature, okay, it is Ricci curvature x at time. We start at time t equal to 0. So Ricci curvature at this has a particular value, okay, and the smallest of this is infimum of this value, which we have not stated here, but in the next theorem or corollary, I will state that. Now, we want to show that that band is preserved. So that's, you have this Rxt greater than its infimum, okay? Infimum is taken all over M. So this condition is preserved all through the flow using maximum principle. And that is what we can see on the board. Yes, this quantity here is positive. Then we can have this heat inequality. We can have this heat inequality. And we can apply maximum principle that we first proved. In this case, it looks like this. The x here is 0, u is r, this function is 0. So you have that. And if the maximum principle we prove for that says if u is greater than alpha, if u is greater at t equals to 0 is greater than alpha, then u is of xt is greater than alpha for all the time. And that is that. If you start this with r x greater than 0 greater equals to the infimum of this Rs, 0, what do you have? We have this. And throughout the flow, you have that, which means this condition will be preserved. All through the flow, you have Rxt is always greater than infimum of Rex 0. Okay? So then we can get a better estimate. Yeah. In this case, let's solve this one so that you can see that. Then we move on. This one we can really calculate this one. This is stronger result. Okay, if R naught here means R naught, what I mean by R naught is X equals to R naught. Okay, together with okay, so you have this and you have this initial condition. Then the theorem says throughout R X T, let me say then, if you have this under Ricci flow, okay, of course, this is under Ricci flow, then this is greater or equal to phi of t, where phi of t is defined as this. If R naught here is negative, you have the first one there. If it is 0, you have phi, you have this greater or equal to 0 all through. And if it's greater than 0, you have the third item there. And in particular, you can see that if R naught greater than 0 at the beginning, the lower boundary of t approaches infinity as time t goes to n over 2r. So if you have R greater than 0, R naught greater than 0, then phi of t, we are going to prove this, approaches infinity as t approaches n over 2r naught. Okay, so this is the theorem. And now let's quickly see the proof. Okay, we are going to apply the maximum principle, but let's put this equation in a good perspective so that it looks like what we can apply maximum principle or comparison principle to solve. So if you look at this equation and you have this guy, unlike what we did the other time, we just say this one is positive and we have this the R dt greater or equals to Laplacian of R. But we can actually write this, okay, in terms of the traceless part of Ricci tensor. The traceless part of Ricci tensor is defined as this. Traceless Ricci tensor is defined as this. Let me put this on top. Okay. It's defined as this. And from here, you square this, you square this. It is easy to see that this square is equals to this square plus 1 over nr squared. So if you square this and you square this, okay, you just have for this place, this is what you have. When you square this, you have the Ricci square minus 1 over n r squared. So this r is a scalar square. So you have this. If you, by that, this is positive, right? So this guy is greater or equals to 1 over n r squared. Therefore, this equation cannot be written as the r dt greater or equals to this Laplacian of r plus 1 over n r squared. So this is what you have now. And you are now saying that together with this. In fact, this one look like this. So you have f except x that is 0. Okay. So except x that is 0. So we can now apply the weak maximum principle. If you want to apply weak maximum principle, you take it to be r. No x, we take x to be 0. Then what in that weak maximum principle we compare with the equation of ODE that we define as a d the phi of t, which is equals f of phi comma t. Okay, with f of 0 equals to alpha. So if you want to compare with this, then we want to define f. We need to define this our f to be this. So, and then we make our f, I will say f of small r now, okay, comma t is 1 over n r squared. So, there we cannot compare. And the meaning of this, okay, let's write the ODE that we are going to compare this with. We want to compare this with ODE. Let's write that ODE out now using this. The ODE is now the phi, the t. Wait, this is, okay. Here is 1 over n r squared. That is Ricci. But you have 2 Ricci square. So there is a 2 over n. So here is a 2 over n, please. And now we can define the ODE that we want to compare a solution with. That's divide the t equals to our f r, which is this one, this guy, is going to be 2 over n pi square, and take our phi at 0, which is equals to alpha. That alpha is infimum of r. Where is it written? Let me put this one. Let's put it as r naught. Okay, yeah. That r naught is the infimum of so we can therefore apply that weak maximum principle. Let's go back to that weak maximum principle now. Oh, good. So we can now apply this. The only difference now is that instead of less or equal to 0 here, it is a greater or equals to the 0 here, and you have this ODE. So if you are having this condition from the beginning now, if it's now greater or equal to RNT, then it's greater than that, which means this initial condition is preserved under the Ricci flow. That is what the statement is saying. Okay. Now, once you have that is the first part, then you can find this phi. That's another thing. You know, we define phi. You can find the value of phi explicitly. What you just need, solve this. This is what you just need to solve. Solve this. Let me give from here. Okay, solve this explicitly. You will have phi to be that. Okay. So this is just integrate this. Okay, you can use expression of variable, you integrate that. phi will be that depending on the value of R0. Either R0 is positive, negative, or equal to 0. So that is a proof of that band on the scalar curvature. And you have some other corollary follow from that. Okay, one of them is that positive or weakly positive scalar curvature is preserved under the Ricci flow. Okay, which is in fact, from that extension here, you have this, that if you start your flow with on manifold with a scalar curvature greater or equal to alpha times t equal to 0, where alpha is positive, then the maximum time of existence is less or equal to n over 2 alpha. Yes, this is just what you have, what we have here. So then you have the other corollary as well. Okay. Then you can do this under volume. Volume. Let's just show one of these so that we can just move on. Volume. Volume of manifold 2. We know the evolution of volume elements. And we have this this corollary based on what we have just done, which says if you have the Ricci flow, okay, on closed manifold, if the scalar curvature is non-negative at t equal to 0, then the volume is weakly decreasing. Then the volume is weakly decreasing. And specifically, the second corollary, if you have this alpha to be less than 0, that is R is greater than alpha, that we said there, that you start with this scalar curvature, which is negative, then this quantity is weakly decreasing. And in particular, you can get this. Okay, let's show one of them. You recall the volume elements, okay? The volume elements, which I will say V of t now because it's time dependent. I write the volume as V, is given by this, the mu, okay, over M, where the mu is just volume elements. The mu itself, I think I give the definition sometimes. Okay, that is the mu. Good. So if I put G here, just to show type G dependence of the mu. Okay, we'll know how this will evolve. Other Ricci flow, the volume elements evolve as minus scalar the mu. Okay, so from there, it is easy to see. Okay, then right here, that V dt is equals to, you have the variation of the volume, so which is integral variation of this, which we already know as this. So you have minus R the mu. So this is volume element of this. So this is what you have. So by this, in fact, this one is straightforward. If you have, you now start the flow with R greater or equals to 0 at the initial time, then the maximum principle says if at the initial time this is greater or equals to 0, then this is greater or equals to 0 for all t in that interval of existence. Let me just say, okay, so you have this. There, from here now, if this is greater or equal to 0, what you have here is that partial t of Vt is less or equal to 0. Okay. So this is in fact, this is a monotonicity formula. And if you just integrate this, let's say from T1 to T2, which are both taken from this interval with T1 less than T2. What you have, if you integrate this, what you have will be V of T2 is less or equals to V of T1. So, meaning that this is decreasing, okay? Weakly decreasing because of less of equals to. So whenever T1 is less than T2 in this interval, you have the volume at time T2 always less than volume at, less or equal to volume at time T1. Okay. So, and the other one too, you can just have that. We already have the meaning for, we have the value if alpha, if infimum is negative, we have that value. Instead of the 0 that we substitute here for this part, you can have, this is what you have, the V dt will be equals to, instead of this one, less or equal to 0, this one for the case, R not less than 0, which we want to prove. So you are using this. This R is that. Okay. So which means R is greater or equals to that guy, which meaning that you have this, you have that minus, which is going to be plus absolute value of R naught over 1 plus 2 over n of absolute value of R naught, okay, together with the volume of T. So from here, this is what I'm saying. I'm substituting from here. This, okay, we have this here. Then from here, this R, when alpha is less than 0, this R is greater than that quantity. And then you have minus R, which is less or equals to this. And you have minus there. So it's less or equals to this guy. And from here, you can just, integrate. If you do that integration, you will have what you see here. Okay, so this guy is less or equals to infinity. So you have it just the way we have this one here. So if you solve that, you are going to have, in fact, you can, that one is clear here. Don't let us try. Solve this. Instead of this one, yeah, it's alpha. Okay. So you can just put alpha here because of that minus here. It is which is the same thing, minus alpha. Alpha is that's R naught. The minus that you have here is taking care of the minus in front of that R. So this one can be alpha, which is negative. So this is what you need to solve. Okay, there's T here. This is with respect to time. So solving this, you will have that quantity less or equals to is 0. So that is monotonicity of that. And you can just you can find the derivative of you can find the derivative of that quantity. This quantity that you have, take the derivative of this logarithm ln of Vt over 1 plus 2 over n into minus alpha t. Take derivative of this, okay, from T1, after that, you integrate, you will have that quantity Vt is less or equals to V naught into 1 plus 2 over n into minus alpha t raised to power n minus 2. So that's how we have that. Then we need to just move on. This is what we have used that one for scalar. Now, if you want to use Ricci tensor, okay, Hamilton develop another one in the original paper, and that's what we use. Okay, so that is called the maximum principle for symmetric tensor, two tensor now. That allows us to go beyond the controlling scalar curvature. We can now use that to control Ricci curvature tensor. And yes, this definition is necessary so that we can define that maximum principle. If you have this quantity, okay, symmetric, and in this bundle, okay, which is also time dependent, satisfy this eigenvector assumption. Whenever you have this omega ij as non-negative symmetric two tensor at point P, okay, if X here is a tangent, is a vector at this tangent vector space such that this is equal to 0, then you have this for any t in this interval. So this is just the definition. And but with this definition, we can now state this theorem. So it looked like, well, what we were discussing before, but in this case, M now, it is not tensor, not the scalar quantity as we have done before. This Mij is a tensor, okay, maybe a matrix. This is called the matrix maximum principle as well. So you have this here, and the theorem says if this tensor is greater or equal to 0 at equal to 0, then it's greater than 0 for all time. So that tensor helps to handle Ricci tensor. You recall that we have Ricci tensor evolving this way, okay? So we can use it. Though there are some issues, especially with this full curvature here, but this can be written, in fact, in a way which look like what we need. Let me, okay. You can write this. Let's say you can have a quantity that can be expressed in a way which will normally, depending on the this Rij. Oh, sorry, I use Ricij. So you can have this, and they look like so it is a way to express this quantity here in form of a quantity Qij. So you can able to state this theorem that, okay, under the Ricci flow, yes, for a closed free manifold now, you know, we said if it's on the two-dimensional, the Ricci curvature just reduced to scalar curvature. Okay, so from three-dimensional manifold, this theorem now holds that the Ricci curvature, non-negativity of Ricci curvature is preserved under the Ricci flow in dimension 3. Okay, there's a remark here. So Richard Hamilton proved that Ricci flow converges to a time metric if the initial metric admits positive Ricci curvature. And in particular, it implies that a simply connected compact free manifold is diffeomorphic to the free sphere if it admits a metric with positive Ricci curvature. We stated this theorem, I think, in the one we still met, in our day 2 lectures as well, the theorem, which is a fundamental theorem in dimension 3. Then for the dimension greater than 3, well, there's still it's still an open problem to show whether the condition on the negativity of Ricci curvature or the sectional curvature is preserved when the dimension is greater than 3. At least we have given for scalar curvature is preserved under Ricci flow in dimension 2, and simply connected compact three-dimensional manifold, the Ricci curvature is preserved here. Okay. So that's what we discussed there. Let's just have a minute break. Yeah. Okay. Yeah, we can continue. Now let's see curvature derivative estimates. So this is another area where maximum principle is also applied. Okay, the aim here is to obtain bounds on derivative of the curvature. Derivative of curvature and not on the curvature itself. We have used maximum principle to get bound, to get some control on the curvature. Then we want to get control on the derivative, yes, of derivative of curvature, okay, under the Ricci flow. We said since curvature under the Ricci flow obeys a parabolic equation with quadratic nonlinearity, we will expect the kind of regularity that is seen in parabolic equation also to apply to curvature. Good. And in particular, we want to show that the bounds on curvature automatically induce, okay, the bounds on the curvature automatically induce a priori bounds on all derivatives of the curvature for positive time. And this is called, in literature, it's called Bastine-Pandolfi derivative estimate. So I will be referring to this as a BBS, Bastine-Pandolfi derivative estimate. So that is what is called in derivative, and we want to establish that one on curvature. So these bands can be used to prove long-term existence of Ricci flow, and in particular, showing that the Ricci flow becomes singular in finite time, and that the curvature must explode as the flow approaches the singular time, which we have demonstrated geometrically in the past days. So the outline here now is want to see evolution of curvature derivatives, okay, and we see Bastine-Pandolfi estimate, then to show that curvature blow-ups at finite time, and possibly how can we extend the flow past the singular time, okay, so that you can have long-time existence of Ricci flow. So we are going to use this star conversion. So meaning that when you have A, B, you sum the pair. So this star will be prominent, okay, in what we discuss next. And the meaning is that you do summation over the pairs of matching upper and lower indices, or you do contraction on upper indices with respect to the metric, or contraction on lower indices with respect to the duometric. Okay. Yeah. Okay, let's see this. This is derivative of Riemannian tensor to the odd power of P. So we now want to see the P iterated covariant derivative of Riemannian curvature tensor under the Ricci flow. Okay, and we see that it satisfies this nonlinear heat type equation. Also, the norm, the square of the norm of this, okay, satisfy this equation 10. Okay, so this P iterated derivative. So we want to prove that. And before we prove that, let's just explain the tools that we use to prove this theorem. Okay. We say, okay, if you have this A-type equation, here A is a tensor quantity, okay, and you have d dt of A equals to Laplacian of A plus B, where B and A, they are tensors of the same type. Okay, then you can show that the square of the norm of A satisfy this A-type equation. Okay, the idea, the reason why we are showing this is that we want to apply, is just this was just a straightforward calculation, maybe like 3 or 4 lines. We can just, let's show that. So if we have this, if A square, forget it can be written as this, where this inner product is a metric T dependent, okay? Maybe we write it this way. This is G of T of A, comma A, okay? If it's evolved like this, we can show that the norm of this, that this evolved by that equation under the lemma. And what you just do is just a straightforward differentiation, okay? You want to differentiate this. So which is you want to differentiate this, okay? And that you do that, you differentiate this. Okay, you do this with AA. Then you differentiate this, where you have this GT, you differentiate this. So you keep this constant, differentiate this, plus keep this constant, differentiate this, is just 2 of this. Partial T of A, comma A. So that is what you have here. And don't forget that we have done this variation of this inverse metric under Ricci flow, which just gives us 2 Rij, 2 Ricci of A, comma A, then plus this is 2. Okay, I will move this GT. This is given already as Laplacian of A plus B, comma A. So this gives us A plus inner product of A, B. So from there, in fact, this can be expressed. You can calculate this, and you will have 2 Laplacian of AA plus 2 ingredient of A square. So you can substitute that here. Then you have that expression. Okay. Also, covariant of A. Covariant of A, find the covariant derivative of A, satisfy that equation. Okay. Okay, let me explain this. This, if you use that star convention, I can write this one as just Ricci star A square. That's how we have that. And using star convention, this is just a B star A. So you have that. Good. Now, if you recall evolution of Riemannian tensor, it cannot be written like this equation 11 we see here. If we use that star convention, okay, all the nonlinear parts in Riemannian can just be Riemannian star Rm using star convention, and you have this part, okay. And from here, we have this corollary, which we can apply this, what we just proved. Okay, let me show. For example, I mean the proof of 12. If we use A as a Rm, that is a Riemannian tensor, and we use B as a Rm star Rm in In lemma 14, we obtain evolution equation 12. Let's show that lemma 14. If you put that here, this, okay, you put Rm, you just A equals to Rm. You substitute that here, and you use B equals to Rm star Rm. So we use A to be Rm and B to be Rm star Rm. Inside this equation, the first lemma, then this is what you have. You have 12. Okay. Then if you use A to be covariant of a covariant derivative of Rm and B to be Rm star gradient of Rm, we obtain evolution equation 13. This 13. That's what we if you apply this. Okay. So good. Now with this, we can now prove the first theorem here. We can prove 9. Okay. And we can also prove 10. So to prove 9, we prove by induction. Okay. So you start with k equals to 0. If k is 0, from that given equation here, so I've written this on the board. Let me write this so that we will not be please. Scrolling. Okay. Let me use k here. This Laplacian. This is of k. Okay. Then plus sorry. K is start from j equals to 0, j. So let's say we have this. Okay. Okay. For k equals to 0, if you put k equals to 0 here, what do we have? We have for k equals to 0, you have, this is a covariant derivative of kth order. So for 0 order means no derivative here. So you just have this equals to, you have this. And for k equals to 0, this is 11. I see 11 here. Because this is k is 0 here. That is this is 0. So you have Rm star k is 0, j is 0. Then k is, that means this is 0, Rm star Rm. So for k equals to 0, you have this, which is 11. Okay. For k equals 1, if you must do that, you have 13. If you put k equals 1 here, you have 13. Okay. Then we can now go for general k. Now assume that this relation would for any given k, apply the lemma. What you just do is that take a to be derivative to the power of k, yeah, and take b to be this quantity. Then when you substitute that, you have this evolution. Okay, this I treated. That is a gradient covariant derivative k here, which is like a covariant derivative to the power of k plus 1. So you have that, which is a evolution equation here. And the reaction term, or the reaction term you have there cannot be written in this form, where you have r plus j equals to k plus 1. Okay, so what you have there, you have this expression, which can be written as this. And that is exactly what we wanted to prove. That's exactly we wanted to prove for k plus 1. If it's true for k equals to 0, it's true for k equals to 1, and it's true for k equals to it's true for k plus 1. That's true for any k. So just take k plus 1 to p. You have the original thing that you want to prove. Then we can prove in a similar way. You can prove the second part of that equation of that lemma. Okay, this is the lemma. We have proved this. We can prove this one in a likewise manner. Then, having said that, this will help us to prove Bastien-Bardot estimate. So we now apply maximum principle to the evolution equation derived in the last section, okay, to get bounds on the derivative of the curvature. This is done under the assumption that curvature itself is bounded above by some constants. If you have this band, okay, on Rm, and okay, we say there are two problems. Why do that? We will say the issue. Let's just leave that. We'll see how to bypass that difficulty in the process. Okay, and this is the theorem. We show this is forth by this. We can apply maximum principle. Once we are able to apply maximum principle, you can get bound on this. And that's what you say. You get bound on this. Okay. Rm is less or equal to C. This is a constant depending on this P. With K is a constant. This constant is a upper bound for K. Okay, if this is less than this under the flow, that is why you have this. So this norm is based on this, the over P over 2. So we can prove this band with type T in this interval 0, 1 over K. 0 is not inclusive. So that is the BBS estimate under the Ricci flow, okay, which allow us to put derivative on, put band on higher order derivative of curvature tensor. And the proof just go this way. Excuse me. Okay. The proof is this. So it's also by induction. If P equals to 0 and in case P equals to 1, yes, we can get that one by induction. If P is 0, you just have P is 0 here, P is 0 here, P is 0 here. Then what you are left with is just this hypothesis with C not equals to 1. So you can now see for P equals to 0 is satisfied. This condition is given, and you want to prove this. So if P is 0, then you have this condition with this. So that is for that. Well, there is an error there. This is a T less than this. Okay. Now for the initial, you start with this. Yes. 1 over K. Okay. For case P equals to 1, then we will get equation 13. We have other time. Okay, it's not here. From P equals to 1, we have equation 13 just like this, P equals to 1, and that is what we have here. So we can now, if you want to apply maximum principle, we already see that P equals to 0 is the initial condition. Let's start with P equals to 1. So with P equals to 1, we have this equation 14 here. That is the same thing as equation 13. Then to apply maximum principle on this equation now, okay, because this quantity now satisfying certain evolution equation. But we have a bad term here, okay, which is it will be very difficult to control, okay, using maximum principle. And even for this gradient of here, we don't have control on it at time t equal to 0. Yes, this thing that we want to get control of at p equals to 1, we don't have this, what this will look like at time t equals to 0, we cannot. So these are the two difficulties that we have. And the point now is, how can we get around this difficulty? We want to apply maximum principle on this, but if this must satisfy evolution equation, we want to say, okay, this is a E-type equation. What is the value of gradient of Rm at t equal to 0? We don't have that. We only have Rm, the curvature now less than k at t of this one, to t in this interval. Okay. Now to circumvent this issue here, what we do now is that we define this quantity. Okay, maybe you call it an auxiliary quantity here, which is this, for some alpha that we will choose later. So you have t here. So this helps us to get control over on this quantity at time t equal to 0. If t equals to 0, for example, this is what you have. You have G, define it as a T. Okay. So for t equals to 0, at t equals to 0, you have G now at t equals to 0. Okay, maybe I should. G is a function on x and t, so that it makes sense. G at t equals to 0, this quantity disappears. Okay, and you have this. So you have this given in the hypothesis of the theorem. So it's less or equals to alpha. This is less than k, is 0. So you can control this. So at t equal to 0, you can have G, okay, x0 is less or equals to alpha k squared. So if we are able to find evolution equation in form of G, then we have this initial condition. We can now control this G. If you can prove that, okay, G satisfies this, and with the initial condition you have this or less or equal to 0, then you will be able to prove that, okay, using maximum principle. So that is the idea. And that is what we have here. So with this choice, we find that the uncontrollable term vanishes as t equal to 0. These are the uncontrollable term, the one this guy, and this gradient of Rm that we want to show here. Okay, so we now have that initial upper bound for G will be alpha k squared. Yes, we get that from the hypothesis. And when t is small, the bad term from differentiating this cannot be controlled by the good term that has this, from differentiating this guy. By that, we can show that G satisfies this. If you put G, you find the derivative of G, and using those all those value that we have at hand, you substitute, this is what we have. So, and using the condition that we are having from initial condition, this Rm less or equals to C naught, I use C naught now because it's Rm less or equals to K, but let's put at CP, okay, is you know the condition on this P of Rm is less or equals to Cp of K over T P2. And then if P equals to 0, you just have Rm less or equals to C naught K. This T to power of 0 is 1. So using that condition, we have this. Okay. And quickly, we can express it as this. If we choose alpha to be this, so this is what we have. And using this condition here, together with it, so this now make application of a weak maximum principle easy for us. We cannot compare this with this initial value problem. Okay, ODE. Okay, solving that, we cannot solve this phi t to give this quantity you have here. So the meaning is that G is less or equals to phi of t, which is given as this. Okay. And it's always less or equals to, we know the value for alpha. Yeah, we know the value for this, taking t to be less or equals to 1 over k from the interval. So you have this. Okay, which is implies that this is less or equals to G, and G is less or equals to this, proving that gradient of Rm is less or equals to Ck over T and a half, T raised to power half. Okay, so this is for K equals to 1. I mean, P equals to 1 now. So we have shown. And to do that for general P, you have to proceed by induction process, which is the thing above. We can just show it for, we can just leave this. So it's true. We can prove for by induction to get for general P and to arrive at exactly this. So that's what we have there. Okay. I think let's just have 5 minutes to round off. Okay, let's quickly do curvature close up at finite singularity. Suppose you have Ricci flow, GT, then we say 0 t is the maximum time interval of existence if either t is finite, okay, or t is infinity. So that is a maximum, okay, we say that time of interval. Though from the what we have seen in the previous time, we say t, we keep our t to be finite. We're talking about finite time. So, and with this, there does not, the meaning of this is that there does not exist any epsilon greater than 0 and a smooth solution G, another G tide, such that T is in this interval of the Ricci flow, where you have G and G tide and G where they coincide for all T. So that's the implication of this. In the latter case, when T is finite, here, when T is finite, what we say here is that G forms singularity at time T. Or you just say simply that G is a singular solution. Okay. If the interval where you can run your flow is just T in this interval is 0T. So you can't, it means at this point, then G at this point, when T approaches this T, that's a blow up, and that's this point of singularity, which we have shown it that you are running your, let's say we give something like this, was the, and as at a particular time, it becomes maybe something of this nature. So this neck becomes a point here because you have a circle, I mean, you have a sphere here, which turns to a point here. So at this point, it's a singular point. This time, this is a singularity time. Okay. So if you have that, you want to avoid this. So then your solution exists in this interval before this particular time. But the point in the Ricci flow is that if you are running your Ricci flow, you want to run it past this time T. so that your solution can exceed, instead of this interval where t is less than infinity, okay, you can actually say t is infinity. Okay, so you have taken that is a long time existence. Okay. So finally, we can now combine curvature derivative band with the short time existence result to prove that curvature must blow up at a finite time. Okay. And the idea can be used to demonstrate that Ricci flow can be extended past the singular time, which we call the maximal time. So this is a theorem here. Okay. So if you start with this mg naught, and the Ricci flow has a unique solution on the maximal time interval of this, where t is less or equal to infinity. So this is the maximum time interval. And if t is a finite, then you must have this. That's the curvature blow up. So meaning that at a finite time, curvature blow up, or you have your solution past this singular time. And the key tool improving this is you have to prove a band on the metric and its derivative. Okay, assume that the curvature is bounded above the constant. Then we can show that the solution of GT converges smoothly to a smooth metric GT. Okay, this is a GT capital. If it converges smoothly to this, okay, it converges this one. We can now start a flow. You know, this is a G. You start with a GT. You are running in on line T, and we get to G. This is a T. T here, and you get to GT. If there's a kind of convergence here, smooth convergence here, then you can now start your flow at this point using this now as initial value. Okay, this is what I say. So you have T, maybe you start with 0. You start your Ricci flow now with G of 0, which is a G naught. Then you have GT. So if you get to the point T, if there's a convergence, if there's a kind of a smooth convergence between G naught and GT, okay, then you can now start the flow again from here, so that this GT become initial value now, and you run it past this. So that is the one of the application after the surgery, just like in some places. Okay, let's see, just leave that. Maybe tomorrow we'll come into that. So, and that is what we are saying here, that you can now apply short time existence using G capital T as initial value now. This helps to extend the solution past this T, which we take as singular time. And that is the advantage of this theorem. So is that if the curvature blows up, at the finite time, okay, then as you have T less or equals to T, then you can have T less or equals to infinity, sorry. So you can run the flow past this maximum, this T capital. And well, this now is a contradiction to that. T is a maximal time, and we cannot have Ricci flow. We exist past this time T. Okay, I think that's where we're going to stop for today. Yeah, maybe let me just show this theorem here, which is this is the convergence of 3. It's a very, very, very good one, and this is a corollary that if GT is a Ricci flow on a closed manifold, and the curvature is bounded, okay, and T is finite, then GT converges uniformly as T goes to T to a continuous metric GT, which is uniformly equivalent to G naught. That's what we say. And we can now use that to prove long-term existence. So that's why we're going to stop for today. Okay. We have our thank you.